Last lecture of this mini course series. So in this course, we've developed like the basics of optimal transport. We developed the calculus on the Wasserstein space. We saw like applications of that to functional inequalities and concentration of measure. And today I want to present an application of this theory to the problem of log concave sampling. So here's the setting. So we're going to have some distribution, pi, which is written in the form exponential of minus v. So v is this potential function as before. This distribution is over Euclidean space. Okay, I'm going to make some assumptions on this potential to give like tractability of this problem. So my assumptions are going to be that v is strongly convex and smooth. And kappa is going to be the condition number, the ratio of these two constants. So this is like paralleling the basic setting in optimization where you have a strongly convex and smooth function. So in optimization, we have precise guarantees for optimizing. And the question we want to ask here is, how do we sample from this distribution? So goal is to output an approximate sample. From the distribution pi. And we have a very natural candidate for tackling the sampling problem. It's the Langevin diffusion that we saw in the previous lectures, because as we said, the Langevin diffusion is a stochastic process which has this distribution pi as its stationary distribution. So if we just run the Langevin diffusion for a long time, then it should approach the stationary distribution, and therefore that will be a good candidate for our sampling algorithm. But what I want to do here is actually like give quantitative non-asymptotic analysis of the Langevin diffusion. So kind of the idea behind this general program is like, can we understand the complexity of this sampling task, even in the basic like tractable cases, to the same degree with which we understand optimization. Okay, so let's recall this is the Langevin diffusion. It's the solution to this SDE. dxt is minus the gradient plus the Brownian motion. But we cannot run the continuous time diffusion on a computer, so we're going to discretize. And so I'll call the algorithm Langevin Monte Carlo, or LMC. So the way we discretize is just the simplest possible discretization. I pick some step size h, and then my iterate is obtained by, well, I take a gradient step from the previous iterate with step size h, and then I need to discretize this Brownian motion over an interval of time of length h. So the law of the Brownian motion increment by definition is going to be a Gaussian with variance equal to 2 times h. Okay, so this is just a basic property of the Brownian motion. So now that I've written this down, this algorithm is very easy to run on a computer because you just have to like iterate this update, and you just need the ability to draw Gaussian samples, which you can do through NumPy or whatever. I guess like technically like you use like deterministic random number generators, but we're going to treat that as like perfectly random. Okay, so we want to know, can we analyze this algorithm for sampling from pi? But there's one important difference between optimization and sampling. So in optimization, we also like fix a step size, constant step size, but we can actually prove in optimization that you converge to the global minimizer under strong convexity. This is not going to be the case in sampling because for any fixed choice of h here, this algorithm, it defines like a Markov chain, a discrete time Markov chain. But the stationary distribution of this Markov chain is not the same thing as the original distribution pi. I mean, like I just did a discretization operation on the diffusion. There's no reason why discretization should preserve the stationary distribution, right? So there's going to be some bias in this algorithm. But what the analysis will do is eventually like control the size of the bias in terms of the step size h, And then you can at least argue that if you choose the step size h small enough, you can get arbitrarily good approximations to the distribution pi. So here's the note. This algorithm is biased, does not converge to pi as the number of iterations tends to infinity. Okay. So let's try to give an optimization perspective on what this algorithm is doing. So recall that the Langevin diffusion is a Wasserstein gradient flow of the KL divergence with respect to the target distribution. So the KL divergence, this was the sum of two functionals. The first is the potential energy and the second is the entropy. So the potential energy is the integral of V with respect to mu, and the entropy is the integral of mu log mu. So from this perspective, although sampling seems like a different field from optimization, when you think of sampling, you think of things like probability theory, Markov chains, and so on. From this perspective, sampling is an instance of optimization. It's just taking place over the space of probability measures, and with respect to this functional and with respect to a certain geometry. So from the perspective of optimization, we should try to understand the properties of this objective function, and then maybe we can do an optimization analysis over the Wasserstein space. So that's kind of the idea, and we've already made a head start because we've analyzed the convexity properties of this objective in previous lectures. But to understand guarantees for discretization, you also need to understand the smoothness. So let's see what you get out of this. So we computed the Wasserstein Hessian of these potential energy functional. We said that if you input a tangent vector grad psi, then you get Hessian of V applied to grad psi. Okay, so this expression was very nice because as soon as, so it tells you that V is alpha convex or beta smooth if and only if V is alpha convex or beta smooth over the Euclidean space. Right? Because if V is strongly convex, then you have a lower bound on the Hessian pointwise, so then it implies this Wasserstein Hessian is lower bounded. And similarly, if the Hessian of V is pointwise upper bounded, then this Wasserstein Hessian is also pointwise upper bounded. So for this potential energy functional, the convexity or smoothness is just the same thing as the convexity or smoothness of the potential function over Euclidean space. Where things get a little bit more interesting is this entropy. We computed this to be the Hessian of psi in the Hilbert-Schmidt norm with respect to the measure of mu. So the nice part about this expression is that it's always non-negative. So we said that the entropy is always a convex functional over the Wasserstein space. So under our assumptions, we have a convex problem. But the problem is, if we were to try to upper bound this quantity, then there's no way to upper bound a second derivative in terms of a first derivative in general. So because of that, this entropy functional is actually non-smooth over the Wasserstein space. So that's one issue to keep in mind when trying to deal with the sampling problem, is that the entropy is non-smooth. Yes. Yeah, L2 mu inner product. Okay, so this was the objective function. Let's try now writing down the algorithm, LMC, in terms of this perspective. So we're going to write LMC as a sequence of two interlaced steps. So the first one, I'll write xk plus This is xk minus the h times the gradient of v. And then I'll write xk plus 1 as xk plus this Gaussian term. Okay, so the reason why I write it in this way is that from this perspective, you can interpret LMC as a splitting scheme. So this first step, it turns out to be exactly gradient descent for this potential energy functional V over the Wasserstein space. Whereas the second part, when I add a Gaussian vector, adding a Gaussian is the same thing as running the heat flow. And we said that the heat flow is the Wasserstein gradient flow of the entropy. So this is a gradient flow for H. So somehow like this is LMC, what it is it's doing like gradient descent on the smooth part of the objective and gradient flow on the non-smooth part of the objective. So this is different from what optimization wisdom tells you to do, because optimization intuition would say, okay, if you have a composite objective function, one has a non-smooth term, then you should use like proximal gradient. So you should do gradient descent on the smooth part and proximal descent on the non-smooth part. The problem is like in sampling, we still want our algorithm to be implementable. So if you just try to write down what is like a proximal step on the entropy over the Wasserstein space, you will not get an easy to implement algorithm. The way that we do get implementable algorithms for sampling is by discretizing diffusions. So this is kind of what we have to work with. And this is maybe like one explanation for why LMC is a biased algorithm. It's because this splitting scheme, like gradient descent plus gradient flow, is also like a biased splitting scheme in optimization as well. So this perspective was like introduced by Andrea Wibisono in 2018. Okay, so this is just some intuition about like how the sampling problem is like similar to optimization, but also like different in some aspects. But we're going to like now like kind of try to actually do an analysis of LMC directly. All right, so there's many different kinds of analyses for LMC, but what I really want to do is like inspired by this connection between convex optimization and sampling, I want to ask like, can we turn proofs for convex optimization into proofs for sampling? Right? And there's a lot of different convex optimization proofs to choose from in the strongly convex and smooth case. And you can try like all the different proofs and see like which ones extend to sampling and which ones don't. Actually, like most of the proofs in convex optimization, there's not an easy way to adapt it to LMC. You can take my word for it. So I will show you like one proof which does manage to like successfully adapt a proof from convex optimization to sampling. So like before we tackle sampling, of course, we should try to understand this convex optimization proof. So let's start with some convex optimization preliminaries. And you know, this is it's not going to be like very novel if you're like very familiar with convex optimization. It's kind of using the same principles in convex optimization, but at the same time, like the analysis I'll present here is also maybe not the most standard one that you'll see in textbooks. So consider gradient descent on the function v, where v is just strongly convex and smooth. So this is just purely optimization now. And gradient descent just follows this iteration where I map each point to by the gradient at that point. Okay, so how are we going to analyze gradient descent? Well, let y be any other point. I'm going to derive an inequality for the next iterate xk plus 1, like the distance away from this point y. And how do we derive this inequality? Well, we're just going to write out the definition of what xk plus 1 is. And then you open up the square. This is like the most like basic thing you can do in convex optimization. So we open up the square and we get something involving the previous term, xk minus y. Then we'll get a cross term. And then we'll get an error term. And then we'll have to understand these three terms. So perhaps the most important one is this inner product term. So the way that you can use this inner product term is just through strong convexity of V. So strong convexity implies that V of y lies above its tangent line. Xk minus y. Okay, so this is just the inequality from strong convexity. And the nice thing about this is it gives you an upper bound for this inner product term, which will be like in terms of some kind of like difference of V's, and then you'll also gain a little bit extra because of the strong convexity. So what happens when you plug this into this bound? So first of all, like this extra term will help you because, well, you're going to multiply this by 2h, and it's going to combine with this first term. So you'll actually get a contraction out, 1 minus alpha h times xk minus y. And then we have also this term coming from the difference of v's. So you have minus 2h times v of xk minus vy. And then we still have the error term. Right? And then, okay, so what's the next step is this term should be the error term because it scales as h squared. It's like kind of lower order compared to the other terms if you think of h being small. In particular, like this term wouldn't be there at all for gradient flow. But in order to do non-asymptotic analysis, you still need to handle this error term, and there's very different ways of trying to handle this error term. They all use smoothness of the function v. So we need a smoothness assumption to do discretization error, and so the smoothness will be used to control this. Here's one way of like controlling this term, and it's just going to be via like the descent lemma from optimization. So let me just recall what you do. Okay, so if I apply the smoothness inequality to v of xk plus 1, then I get this quadratic upper bound. Where this difference, xk plus 1 minus xk, this is minus the gradient. And similarly, this squared term is also a gradient. So if you look at this inequality, basically like as long as h is smaller than 1 over beta, the smoothness constant, then this middle term is going to dominate. So h less than 1 over beta is going to imply that v of xk plus 1 minus v of xk is bounded by minus h over 2 times the squared norm of the gradient. So this is called the descent lemma in optimization. It tells you how much your objective function has to drop after one step of gradient descent, assuming that you're smooth and your step size is not too big. Okay, so this is very fundamental fact in convex optimization. What it lets us do is upper bound the size of the gradient, because we can now upper bound this by 2 over h times v of xk minus v of xk plus 1. Yes. Okay, I think that's right. So then if you look at what happens here, what's going to happen is that this v of xk is going to cancel this v of xk. And so this term kind of just replaces this v of xk by v of xk plus 1. So let's write out what that is. And we get this inequality. So this inequality might not be like the one you've seen before for analysis of gradient descent, but it's pretty fundamental. So in optimization, you usually take this extra point y to be the minimizer x star. So this inequality contains like a lot of information. One case is like the strongly convex case when alpha is positive. So when I take y to be the minimizer, this term is just non-negative and I can ignore it. And then I get a contraction in the distance to the minimizer. So that's the strongly convex case. In the case where alpha is 0, so I'm just like, I'm convex but not necessarily strongly convex, then this coefficient becomes 1 and I can still get a rate of decay by telescoping this inequality. And then you will show that this objective gap decays at a rate which is like 1 over the number of iterations. So this inequality handles both. I'm going to record it because it'll be important later. So that inequality is valid for all h that satisfies this condition. Yes. So I'm going to label this EVI. It stands for evolution variational inequality, just because like this is a name I've seen for it in this book by Ambrosio, Gigli, and Savare, but it's just a name. So this is an inequality for gradient descent. Yeah, fine. All right. So as I said, in optimization, like we usually use this inequality where y is taken to be the minimizer. Actually, for sampling, it'll be very helpful that this inequality holds for all choices of y. By the way, like the original reason why it was important to consider different choices of y is because if this inequality holds for all y, and you take like the limit as h goes to 0, this actually characterizes the gradient flow. And this characterization of the gradient flow has nothing to do with differential structure, so this was used to like define gradient flows on metric spaces. Anyway, that's why it comes from this book by Ambrosio, Gigli, Savare. Okay, so what we're going to do in sampling is we're going to show that the Langevin Monte Carlo algorithm satisfies this kind of inequality, but with an extra error term. So let me write out what this inequality is. So this lemma is for Langevin. And mu k is like the iterate along Langevin. Beta d h squared. Okay, so this is what we're going to prove in this lecture. So yeah, you can see this is like exactly the analog of what we have in Euclidean optimization, but there's this extra term. This extra term like needs to be there because, as I mentioned at the start, unlike optimization, LMC is biased. We cannot hope that the error is actually going to tend to 0. Instead, we have this extra error term, and we're going to see like how this controls the bias. And yeah, so I said that this EVI inequality in optimization was very useful because it lets you like deduce rates of convergence in both the strongly convex and weakly convex settings. So in the same way, like this lemma for sampling, you can just iterate it and you will get results. So also like for the weakly convex case and so forth. Let me just show you like one quick corollary of this lemma in the strongly convex case. The ambient dimension. Yes, this is not dimension free. And yeah, indeed, like all the upper bounds for sampling do have some dimension dependence. What will play the role of D in what? Oh, well, like if you, the book on gradient flows on metric spaces, it was considering like continuous time flows. And then like you wouldn't have an error term. Like, first of all, like LMC is not really like gradient flow. It's like some discretization of the gradient flow, not even like gradient descent, but some other discretization of it. Yeah, and it's for this discretization that you don't get the EVI like in Euclidean space, but with the error term. Yes, sorry. Good, but one quick corollary of this is just like this KL is always non-negative, so let's just drop it and then let's iterate this inequality. So what happens if you iterate it? Well, the W2 squared, let's say I run for n iterations, then I'll get 1 minus alpha h to the power n plus, and then this error term times like a geometric sum. This you just get by unrolling that inequality and dropping the KL term. And then you can evaluate what this geometric sum is. It's of order 1 over alpha h. Okay, and now I'm going to multiply this whole inequality by alpha. And the reason why is because the W2 squared is like not actually a scale invariant metric for this problem. I just wanted to make things scale invariant. So turns out that alpha times W2 squared is the natural scale invariant quantity. And for this quantity, okay, you have one term that decays exponentially fast. And then you have the bias term, which scales like beta times dh over alpha. Oh, no, sorry, there's no alpha because I multiplied the whole thing through by alpha. Beta dh. Okay, so the interpretation of this inequality is that this first term is decaying exponentially fast. So imagine that I let n go to infinity. This first term will disappear, and this is an upper bound on the bias, like the Wasserstein distance between the stationary distribution of my Markov chain versus the distribution pi that I want it to be at. So this is an upper bound on the bias. If I want this whole thing to be less than, let's say, like epsilon squared, then this tells me I can choose my step size to be like epsilon squared over beta times the dimension to make this second term less than epsilon squared. And then you can choose the number of iterations, capital N, to make this first term also less than epsilon squared. So finally, what you get out of this is like the number of iterations in order to make this scale invariant quantity, square root alpha times W2 with respect to pi. I can make this quantity less than epsilon for a number of iterations, which is kappa times the dimension. So this is a condition number over epsilon squared times log of the initial distance over epsilon. Okay, you don't have to like stare too hard at this expression. It's some like non-asymptotic complexity bound. Maybe even like forget about the log terms for now, but this is like basically condition number times dimension divided by your target accuracy epsilon squared. So it's like very nice that we can get precise like non-asymptotic guarantees for sampling. Compared to optimization, the rates are worse. Like in optimization, because you don't have this bias, you wouldn't have this polynomial dependence on 1 over epsilon, you would have linear convergence. And also in sampling, we have this extra dimension dependence. But nevertheless, we're able to still like say something. And let me also mention, like, there's different kinds of analyses for Langevin Monte Carlo, but out of like all the proof techniques I know, this is the sharpest result. Like no other proof technique that I'm aware of actually gets you linear dependence on the condition number. Everything gives you like kappa squared. So this is like one instance where the calculus on the Wasserstein space actually like really helps you for the analysis. Mm-hmm. So yeah. Mm-hmm. Good. So beta is the smoothness only of this part. Yep. Okay, good. So first of all, let me make the point that when we like design algorithms for sampling, it's not like we have all the like building blocks for algorithms available at our disposal, because we still need to implement an algorithm at the end of the day. So somehow like what's forced upon us is this like discretization of Brownian motion, which turns out to be the gradient flow of entropy. Now this is something that I like to think of as both the blessing and the curse of sampling. So why is it a blessing? The blessing is that for the non-smooth part of the objective, the ingredient that we have available to us, the gradient flow succeeds without the use of smoothness. So in some sense, this is like the reason why sampling bounds are even possible in the first place, is that we have access to some ingredient that works for non-smoothness. But what is the curse of sampling? The curse of sampling is that what we have here does not like match what we have available up here. And because these two do not match, then sampling leads to bias. And of course, there's like more sophisticated things you can do to try to like eliminate the bias. This is like the simplest possible algorithm, but yeah, it's still very fundamental, so I think is worth analyzing. If you have available the proximal map for the non-smooth part. Yeah. But if you think about what is the proximal map for entropy here, that's like not really implementable. I'm happy to discuss afterwards. Okay. I think you're right. Yeah, I think you're right. Mm-hmm. Yes. Do a different V. Yeah, so the Langevin diffusion is not the only diffusion that has stationary distribution pi. Yeah, so there are like better sampling algorithms, like better complexity guarantees than this. But yeah, this one like is fundamental in the sense that it is the sampling analog for gradient descent. And gradient descent is the first thing we learn for optimization. So this will be the first thing we learn for sampling. Did that answer your question? Okay. All right, so let's see. Okay, I have like maybe 20 minutes. We can try to prove this lemma. I think I won't need, well, I'll just keep it there for a little bit. Okay, so our focus is just going to be to try to establish this one-step inequality in this lemma. And to do that, we're going to like do some like calculus on the Wasserstein space. The intuition for it is just going to be like, based on this, I split the dynamics into two parts. One part is supposed to be like for V, one part is supposed to be for H. So there's going to be like three parts to this proof. The first one is showing that this first step actually dissipates the V functional. The second step is going to be that the second step dissipates the entropy functional. And the third step is going to be like that they don't interfere with each other too much. Actually, I'm going to do like steps 1, 3, then 2. Okay, so let's just do it. So the first part, I just want to argue that the gradient step dissipates the potential energy. And actually, like, if you think about it, this is just a corollary of what we did on Euclidean space. Why? Because this gradient step here, this is nothing more than just like literally like Euclidean gradient descent on the function v, and also this function v, this potential energy over the space of measures. This is the same thing as the expectation of v of x, where x is a random variable drawn from mu. So step 1 is just literally like taking what we did for Euclidean space and taking expectations. So let's see how that goes. Let's say x, k, and z are going to be optimally coupled for the Wasserstein distance, where xk is my iterate at time k, and z is a draw from my target distribution pi. Okay, now I'm going to just apply this EVI inequality. That's why I kept it up here. I'm going to just apply this EVI inequality where, well, like xk becomes like capital xk, xk plus 1 becomes, well, xk plus after I take the gradient step, and y is going to be my random variable z. So this is why it was important that this EVI inequality holds for all choices of y, not just the minimizer, because we're in the sampling setting, we're going to take it where y is this like random variable z. And then we take expectations. So what do you get? So the first term is xk plus minus z. And then I have xk minus z. And then I have minus 2h times the expectation of v of xk plus minus v of z. Okay, this is just from the Euclidean EVI. Okay, now we can interpret these terms. So I chose xk and z to be coupled optimally. So this is just the Wasserstein distance between mu k and pi. Good. Over here, like xk plus and z might not be optimally coupled, but at least it's a suboptimal coupling, so this upper bounds the Wasserstein distance. And then finally, by the definition of the potential energy functional, this thing is just v of mu k plus minus v of pi. Okay, so I'm going to write down this inequality that we proved over here. So this is going to be our first of 3 inequalities. And of course, like in order to apply the EVI, I needed the step size to be smaller than 1 over the smoothness. Good. So this part, there's like nothing like Wasserstein-like going on there. It's just Euclidean optimization. Okay. So now the second step, I'm going to argue that the second step where I added the Brownian motion, in other words, the Gaussian random variable, it's not going to increase the potential energy too much. Let's say heat flow doesn't increase V too much. So this is a simple consequence of smoothness. So what do I want to bound here? I want to bound the difference between mu k plus 1 and mu k for the potential energy. So remember, like mu k plus is after I took the gradient step. This is where I add the heat flow. So I'm just trying to say like how much worse did the heat flow make things for me. But this is just the expectation of V of xk plus 1 minus V of xk plus. And now I'm just going to apply the smoothness inequality to V. So when I apply the smoothness inequality, I will have this quadratic upper bound. Okay. And now, if you look at what's going on here, this is the difference between xk plus 1 and xk plus. This is the Gaussian that I've added. The Gaussian that I've added is independent of my previous xk plus. So actually, this first term just disappears because it's mean 0. And here, I have the Gaussian. So this is like distributed as n02hi. So when I can just compute the expected squared norm of this. And this will give me beta times dH. Yeah. So that was step 2. Let's just write this down. Not so bad, right? We're already like 2 out of 3. The last step is the most subtle, and this is where we're actually going to need to know some things about Bose-Einstein calculus. So step 3, heat flow dissipates the entropy, which is pretty natural. So what do I want to do? I want to like so this is going to be the goal of this step, is I want to bound like how much this Wasserstein distance changes in the last step, the heat flow step. So like in order to do that, I'm going to introduce like the heat semigroup. This is just convenient notationally. So what is the heat semigroup? If I apply this to a measure mu, this is the same thing as mu convolved with the Gaussian of variance 2t. You note my convention here, 2t. Okay, so the here, like I can write mu k plus 1 as just, I take my mu k plus and then I run the heat semigroup for time h. And I just want to look at this difference. So what is the natural thing here? It's just to differentiate this Wasserstein distance along the heat semigroup. So I want to differentiate this squared Wasserstein distance. Now, recall that the heat semigroup, this is just the Wasserstein gradient of flow for the entropy functional. So this is asking like, how do we differentiate the Wasserstein distance along the Wasserstein gradient flow for the entropy functional? And very conveniently, Yair actually did this computation like 2 lectures ago. So he showed precisely that this derivative is equal to twice the inner product between, well, you have like the Wasserstein gradient of the entropy here, I guess evaluated at this measure, times like the gradient of the squared Wasserstein distance, but the squared gradient of the squared Wasserstein distance was this like transport map. It's the optimal transport map from this measure to the second argument pi. And this is all under the mu k plus qt inner product. Okay, so if you don't remember, then take my word for it, or like, I wonder, yeah, check your notes for Yair's lecture. Okay, so we have the gradient of the entropy, which is what this argument was following, times the gradient of the squared Wasserstein distance. But now we're going to use the convexity of the entropy functional, again, to bound this inner product term. So the convexity of the entropy functional tells me that h of pi is an upper bound for h of mu k plus qt plus exactly this inner product term. So this t is the same t here. Okay, so this gives me an upper bound for this time derivative. This is going to be bounded by 2 times h of pi minus h of mu k plus qt. So this is from convexity of entropy over the Wasserstein space. We have this differential inequality, but I can simplify it further by noting that along the gradient flow of the entropy has to be decreasing. So this is some like intermediate time along the gradient flow. The entropy has to be bigger than what it will be at the end of the gradient flow. Oh, sorry. Yes, this is one derivative. Great catch. Okay, so because entropy is decreasing, I can lower bound this term. And now, like when I integrate this from time 0 to h, I will just get this difference here. This difference of Wasserstein distance is upper bounded by 2 times the length of time over which I'm integrating times h of pi minus h of mu k plus 1. So I'll write down this third inequality over here. Okay. So let's say that you believe me for the derivation for these 3 inequalities. I claim we're done. Just have to like combine these 3 inequalities to get the lemma. So maybe we can like stare at this and try to see why that's true. And I'll give you a minute. Yeah, so, okay, what you should get is like you just like multiply this inequality by 2h, you add it to this one, and then you also add it to this one, and you'll get precisely this lemma. And as I mentioned before, this lemma, you can iterate, you can get guarantees for the Wasserstein distance in the strongly convex case, you can get KL guarantees also, you can also handle the case where alpha is 0, and it's a weakly convex case. And you can extend this like a little bit further to other settings, but overall, I would say this proof is like a little bit special actually to the structure of LMC and its interpretation over the Wasserstein space. So this like basically concludes the content of this lecture. It serves as an introduction, I guess, to the analysis of sampling algorithms in general. So LMC is like the most basic sampling algorithm. If you actually do MCMC, then you want to consider things like, what if I add like a Metropolis Hastings filter to correct for the bias? Like, can I like get more accurate discretization schemes than just these basic ones? Are there like other stochastic processes that do better than just Langevin? So all these kind of questions are like answered in the literature and more, and still active area of research. In particular, like I would really like to understand what is the optimal complexity in terms of like the number of queries I need to make to this potential and its gradient in order to output a sample. And that question is still like unresolved. Like we don't have matching lower bounds. We also don't know if acceleration is possible for sampling. So it's just a teaser for some of the open questions in this field. All right, I'm done.
Any questions?
What? Right, so the best upper bound in W2, like that criterion, would be like roughly kappa d to the 1/3 over epsilon to 2/3 times like some log factors. And actually like this is only known in W2. Like if you ask about KL, then the best known is like worse. Yeah. So far, like no lower bounds have been exhibited to show that polynomial dimension dependence is necessary for sampling in this context. So first you replace the Langevin diffusion with something called the kinetic Langevin or the underdamped Langevin, which is like it's kind of like the sampling analog of Nesterov's accelerated gradient descent. So you take this other diffusion process and then you kind of discretize it with like fancier discretization methods. But that algorithm, like as you can see, still gets like linear in condition number. If we had acceleration, you would expect square root. Non-convex V. Okay, so we can do analyses, let's say when pi satisfies like a log Sobolev inequality or Poincare or something like this. There's also some examples of like structured situations where it's like still non-convex, but you might be able to say something. Yeah, I mean, if you like allow like arbitrary non-convex potentials, of course it will take exponentially long, but you can still ask like, are there special cases where you can get polynomial